There were not a whole lot of examples in that whole section, so I went ahead and did a couple to go over some stuff for you. So this is example number 31. It's homework page 262. It says prove if A is invertible, then the determinant of A inverse is equal to 1 over the determinant of A. Kind of a nice result. So when you're asked to show something like that, sometimes it's nice to do a simple case, like try a simple case that you know is invertible. Now, and you can use your calculators to use it, maybe do a couple things by hand here and there, depending on the situation. So you can easily check now if a matrix is invertible just by taking the determinant. Or you can just hit the 1 over x button on your calculator like that. Some of them just have that button, and it'll give you an error if it's not invertible, but rather you use operations to test it. So I just did 1, 2, 3, 4. It's my favorite 2x2 matrix, and just did the calculation. So this is what I would want you to do on your calculators is find the determinant. That you can do by hand, obviously, and then you know that 1 over the determinant is by the theorem is the well, that's I guess what we're showing. So that's the property. Then find the inverse of A on your calculator or by hand, and then hit a determinant, and you'll get negative 0.5. So I tried it on mine, worked out good. Okay, so then to do the proof, say proof, assume A is invertible. So if A is invertible, we know A inverse times A is equal to the identity matrix. So you start off, now remember, determinant is a function that converts a matrix to a real number. So it's like mapping matrices to the reals. So so 1 is equal to the determinant of I, and I, as we just shown, is determinant A inverse times determinant of A. Now, by the property we proved above, or theorem, I forgot what theorem it is, you can separate those determinants. It's determinant of A inverse times determinant of A. Very nice property. So from there, it's almost done. So just carry out the next few steps, and you'll get the result above. It's like one more step. You can easily show that. So maybe you saw that already, but you can write it up more carefully now. Number 32 is not assigned, but I thought I'd go over it with you. If A and C are n by n matrices, and then it's just saying that C is invertible, then the determinant of A is equal to the determinant of C inverse AC. So essentially, we'll be using the property of separating determinants by one at a time. So from here, what you can do, as you can probably see, is you can take the determinant of each of those separately. Once you do that, then you're in the reals. Once you're in the reals, that's it's actually called a field, but you have commutativity, so you can commute and then go back. So maybe you can see that right away, but you get determinant of C inverse, determinant of A, determinant of C, and now we're going to regroup these together. So we're going to commute because they're real numbers, and you get that's equal to determinant C inverse, determinant C, determinant of A. Now you go back, and that's determinant C inverse C, determinant of A. But determinant of C inverse C, which we know exists, right, is I. So that's determinant of the identity matrix, determinant of A. And we know the determinant of identity matrix is just 1. Product of diagonals, if you want to think of it like that. And so we get it equal to the determinant of A, which equals determinant, or 1 times determinant of A, which equals determinant of A. Okay, so that's a nice little result. We will see later in the book this form. It's a special form we'll talk about when we get there. I'm not sure when, but I recognize that form. We'll talk about it more. Okay, let's go ahead and go on to 4.3. I did some write up on this one already, so go ahead and you can pause and write it up, and I'll just talk about it. Not a whole lot here, and then we get to Cramer's rule, and we'll go over that one as well. So let A be an n by n matrix. Then so I know you have your calculators and all that, and you can use them, but you still want to know how to apply these properties, if nothing else, for future theorems and results you get to understand how things work. So that's why you want to do it. So so to take the determinant, so to compute something like this one down here, this example I already have written, this is a 1, 2, 3, 4, it's a 4 by 4 matrix. So a 4 by 4 matrix would be quite tedious to just take the determinant. But if you do these operations, 1, reduce A to echelon form, not reduce, but just echelon form, using only row addition and row interchanges. So multiply by a row and then add by a row. Or you can interchange a row if needed. And then 2, second, if any, we know this already, if any row or column is all zeros, then we know the determinant of A is equal to 0. So once you've done that, then the determinant of A is -1 to the R, where R is the number of row interchanges, times the product of the pivots, which is nice, right? It's the diagonal. So if it's invertible, right, you won't give any of those to 0 out, and you just keep track of the interchanges. And you do it as you go, actually. So here's an example that I did. Went ahead and just copied it over, took a picture. So you start with A. First factored out 2 in that first row. Okay, and then from here to here, we went ahead and added rows. Right, so from there to there, we did, I didn't show it that step or write it up, but it looks like I did the 3 and the 2. So multiply and add appropriately to get those to 0 out. And that doesn't change your matrix, right? That doesn't change your determinant. I mean, then from here to here, so from this step to this step, we did a row interchange. So when you do a row interchange right here, this one and this one, so 2 and 3, we did a row interchange. That brings out that makes it a negative. So you just factor out that -1. And then from here to here, again, it's a row operation, so it doesn't change anything to 0 out this entry. And then the last entry I went in and wrote it down. The last entry is -8 row 3 plus row 4, so to give you a 0 here. Back up here, what do? We factored out a 2 right there on row 3. Okay, so that's where that comes from. So then you end up just getting, so you keep track of the row interchanges as you go. And then the last, once you have the row echelon form, you can see it's just the product of those diagonals. So it's really 1 times 1 times 1, and then times 17. Okay, you multiply that out and you get negative 68. So practice a few of those using the properties by hand, because it gets you used to the properties. That's really the key there. Okay, let's go on to the next theorem or concept, which is Cramer's rule. If you may have seen this before or tutored it or something in college algebra. We do Cramer's rule in college algebra, and it's using determinants to solve systems. So let's go through the statement. Let AX equals B be a linear system, and it's assuming that A is an invertible matrix, which is huge, right? So if it's an invertible matrix, and has unique solution and all that, but that's the key, is that it's invertible. X we define to be that column vector, B the other column vector. Then the system has a unique solution given by this. So each be like x, y, z, or x1, x2, x3, whatever, however many equations you have. It gives you the solution to that value. So what you do is you take the determinant of B sub n over the determinant of A. So the determinant of A is the coefficient matrix. Okay, and then B, what you do is it's the matrix obtained by replacing the kth column of A with B. So the solution, K, so suppose this is like x, y. So if this is a y, it would be in the y position. You replace that with whatever column B is. So for my little example down here, it's going to be CF. That's your B. So let's do this in general for a 2x2 for my example down here. So what you have is A equal to A, B, D, E. So that's your matrix A. And then your X is really just your XY. And then your B is CF, to mimic what we have above. So the solution X is the determinant of B1, because that'd be like the first entry, over the determinant of A. So B1 is going to be the matrix, it's the determinant of, so you're replacing the CF right here for the first entry. And then the second entry, you're replacing that right here. So it's going to be, make it as a column, CF, and then BC, or BE. So it's that determinant over the determinant of A. A, B, D, E. So the determinant of CEBF is just CE minus FB. Determinant of A is AE minus DB. And so if you have actual numbers, you just do that calculation. And you already know that determinant of A is non-zero. Okay, so you can say that in there, although because you're assuming it's invertible, it has to be non-zero. So usually I can't help but actually say that right here. And then your y, same thing. You just do those determinants. So it gives you kind of an algorithmic straight up way of solving a system without doing all that row reduction stuff. So this determinant of B2 over the determinant of A. So determinant of A is the same, won't write that one out. Now I'm going to say the determinant of the matrix. So now it'll be AD, and then you replace and get CF here. Okay, and then that's determinant of A is the same. So you get the matrix or value AF minus ED, and then determinant of A is the same, AE minus DB. And I'm being a little lazy on the commuting properties there, but they're all the same, of course. So try this one, doing the same process. Let you work it out. Solve the system using Cramer's rule. So the system is x1 minus x2 plus x3, x1 plus 2x2 minus x3, that's equal to 0, and then x1 minus x2 plus 2x3 equal to 0. So that's your system. And I'm going to write my matrix A down. And since I don't have the solutions there, I'm going to make sure and check to see that this is non-zero when I do that determinant. So it's 1, negative 1, 1, 1, 2, negative 1, 1, negative 1, 2. So there's your coefficient matrix A, and I'll go ahead and try that. Once I know that's non-zero, then I know it has a unique solution. And you can't really tell by looking right away. So 1, negative 1, oops, negative 1, 1, entering in the matrix, and then 1, 2, negative 1, 1, and 2. Enter, double check, 1, negative 1, 1, 1, 2, negative 1, 1, negative 1, 2, and take its determinant, and I get the determinant of A is equal to 3. Okay, so do the rest of that, see what you get for the solution. I'll probably not write that up. Just remember you're replacing the 0, 1, 0 with whatever variable you were solving for. So for x1 it's there, for x2 there, and for x3 here.